Hello from Daytona State College. It's Dr. Ron England here, and today's programming video is how to solve iterative-based solutions through recursion. I know I've got a whole lot of words there with a whole lot of syllables, but I think we can figure this out. So let's say you're in your engineering space, and all of a sudden you're confronted with an equation that looks like this one. Y equals the log of x, in this case it's the natural log of x, plus the tangent of x. And you're not solving for y, you're solving for x. You know y, but you don't know x. Okay, so there's your equation right there. Now, I'm showing it to you in terms of the Python code, but it doesn't matter. It's still y equals natural log of x plus tangent of x. X is going to be in the x portion there, and the tangent would be in radians. So how can we solve this? Well, the first thing I'm going to do with this is I'm going to plot it. And of course, you know what? I got my pen, I got my paper, and I got a couple hours to kill. I can start plotting this, but you know what? I don't need to do that. I know Python. I'm going to use Matplotlib and NumPy to make life easy on myself. So first thing I'm going to do is I'm going to import those two libraries up here into Python. Wow, it's done. Now they're imported. Now, a quick way to do this. I am going to first set up a bunch of x values and then set up a bunch of y values. So I'm going to use a function in NP called linspace. I could have used arange, but I'm going to use linspace because I'm going to demonstrate both of those to you. So I'm going to highlight both of those suckers, and I'm going to control enter it. And now if I come over here to my variable explorer, I can show that x is going to go from 0.1 up to 1. And in this case, there are 100 steps in the x. In other words, what it did is it took my values from 0.1 to 1. I had 101 there. That's how many numbers I wanted it to spread it out over. There it is. Okay, so I got my x, and it looks like an array. Kind of is an array, but it's an array created by NP, so it's got a few things it can do that are pretty neat. Now, the funky thing about this y here is because I set it to x, and x was an array, look what it does with y. If I go over here to look at my y's, it's all the values of the calculation from good old 0.1, which is going to be equal to the value of the equation is negative 2.20225, all the way up to where the x equals 1 and the y equals 1.55741. Now that alone is going to help me do a whole lot of stuff. I could probably figure out, given any y, what the x is just by sitting there and trial and erroring it and trying things in. But I'm going to show you some ways to do stuff like this that kind of make your life handy. Now, I could just use the good old Newton-Raphson routines built into NumPy and be done with it. But then that wouldn't be writing the code to make this, and then my video would be done in 4 minutes, and you wouldn't have really learned a whole lot of some programming. But the first thing I'm going to do is I'm going to plot it. Now here's a nice thing. I got an x, I got a y, wazoo, control enter, and voila. I'll bring it over here so you can see it. I got a plot right there. Isn't that nice? In fact, I'll squish it down a little bit, bring it up a little bit. You can't see it now because it's squished down, but there is a plot of that. You can see all those values right there. Well, that was kind of nice. All right, it's 4 minutes into this video, and I've already plotted this pretty fancy function here. I've done quite a bit. But now let's say I want to, by using some iterative technique, I want to solve for any given x given y. Well, we know what I'm going to do first is I'm going to go ahead and define that function as an actual function. So I'm going to be fancy. I'm going to call it f of x because, well, you know what? We do f of x all the time in mathematics, so I might as well call it that. Highlight, boom. Now, it's a function. It's in the memory of my Python. It's there. Now comes the hard part. I need to write a routine that will iterate in on the solution. Let's first think about how you would do this. You know, how do you iterate in on the solution? When I say iterate in on the solution, it's got to mean something. So here's what we do. This is the guy with the calculator. He sits down. He needs to figure out what it is. So he goes, you know what? Let's try x equals 0.4. And let's go click, 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 click. And I come over here, and you know, if I do that on the calculator, it's going to be somewhere between negative 0.5 and 0. So I'm going to get a number that's kind of in here. And I'm like, oh, well, that's not the one I was looking for. I want to know what the x is when y is 0.5. So I come over here a little bit further, and I try a higher number, and then I just kind of iterate down. And I might be doing a whole lot of playing with a calculator just to get to where I want to be. But regardless, the methodology here is going to be pretty much the same. Now, there's a lot of techniques for finding solutions to equations this way. Good old Newton-Raphson is going to take you there. But I want to show you just a methodology that is a common trial and error methodology. So let's spread it out so you can see the code here. And let's show you how you would write code to do this. And I'm going to call my function here T and error, trial and error. So when I think about the trial and error, there's a few things I need to know about what I'm doing here. First is I'm going to start at some x, and I'm going to go to some x by some step. Okay, so in other words, let's say I'm going to start at 0, I'm going to go to 1, and I'm going to go by steps of 0.1, and I'm going to plug it into the calculator until I get to the y that matches the y that I want, which, by the way, in this case is the target. Now, if I do it by steps of 0.1, I'm only going to get so accurate. So I'm going to have this little guy here in my function called accuracy. So I'm passing 5 things to my function here. Start, max, step, what the y is that I'm looking for, and how accurate do I want to be. So the first thing that I do is I create, in this case I made an I. I called it I could have called it anything, but I called it I, and I use the NP A range. It's not a range, it's a range, like Aaron, a range. What it's going to do is it's going to take your start and your max and your step, and it's going to put a whole bunch of numbers, just like that other one, that good old linspace. It's going to make an array of those numbers for you that are at the start at the start, and at the max, and have that same step in between them. Okay? Got it. Now, next thing I'm going to do is I'm going to start a loop. This is a loop for x guess in I. In other words, I'm going to go through every value in this array that I created with my A range, which starts at start and ends at max and has the step that I gave it. I'm going to go through each of those, and I'm going to do y. I'm going to calculate a y guess. Well, the y guess is easy to calculate if I've got the x guess, because the x guess, I just plug that into the function up here that I made. That's why I defined it as a function. I could have put the equation down here too. It would have worked the same way. But what if I want to change something in the equation? What if I want to add, divide the tangent by 2? Well, I guess I could divide the tangent by 2 down here, but I could also, I could change this out. I can make this function whatever I want to be. It's going to work for any function that increases as x increases. That's a big limitation, but it's not a limitation that's a problem here because we plotted it. We know it's increasing. Okay? So it's going to work. So here's what I do. Okay, I said, okay, I'm going to guess an x. I'm going to calculate the y. I'm going to look to see if the y is close to the one I'm looking for. and you know what? If I'm within the accuracy, I'm going to go, I found it. Now, while I'm doing this, I'm actually going to print all this stuff out too, which kind of makes it so I can print out all my guesses. So here's the situation. Look at this. If np.abs, these aren't abs like six-pack abs, like, I'm doing lots of sit-ups. This is absolute value, okay? Has nothing to do with your stomach. It's abs, alute, not abs like abs. If the difference between the guess and the target is less than the accuracy, you're close enough that you're there. You got it. Sweet, you're done. Okay, so you return the value that you guessed. Okay, now in this case, I returned I. I don't need to return I actually just need to return X guess. I can make a change there. Booyah, I fixed it. X guess. Now that's what's going to get returned is the answer that you had as the guess for, what, so because why? Because the X guess was the right guess. But what happens if it goes past the Y, the target Y you're looking for? You overshot it. Uh-oh. You overshot it. What are you going to do if you overshoot your guess? Okay, you're going through this equation and blah da 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 da, and you make your guess and you go past it, and then you make the next guess up, and now you've overshot the whole thing. Well, guess what? You overshot it. Well, what do you do if you overshoot it? We got a good plan for this. We're going to back up to the last guess, and we're going to take smaller steps. How do you do that? Well, that's actually not that hard to do. But look what I'm doing here. I'm calling the function t in air. But I'm calling it with new arguments. I'm taking the guess and I'm subtracting out the last step. I'm going backwards one step. I'm going to still go to the same max, but x steps divided by 10. I'm going to reduce the step size by a factor of 10. I could have reduced the step size by a factor of anything, really. It's just I picked 10. I got the same target. I got the same accuracy. Those things are going to be the same. And then in this case, if I make it past all of that, I know the number is past all the stuff. It's, I can keep going, but whatever the answer is, it's past X max. So I'm just going to return X max. So I take all this guy in, I go booyah, I'm now in the memory, and zoop, it's in there. Now, all I got to do is call it. That's it. I got to call that function. So let's say I'm looking for, now look, see where target is argument 0, 1, 2, 3, 4. It's argument 4, 1, 2, 3, 4. So I'm looking for X or Y equals 1. Now, you can come up with a pretty good guess right off the bat by looking at this. Okay, so where Y equals 1, come across, it's 0.8 something here. So I'm kind of expecting the answer to be somewhere between 0.8 and 1. I mean, I'm going to think it's probably closer to 0.9, somewhere in that range just by eyeballing it. But you know what? I wrote my code. All I got to do is say, I call it and assign the answer to answer, control enter, and oh, look at that. Isn't this sweet? I had printed the stuff out, so I can actually look to see what it did. All right, it guessed 0.1, and Y was negative 2.2, and the target was 1, so I increased X, and I increased X, and I kept going. But at some point, when I got to 0.9, I overshot it, so I backed up to 0.8. And then I got to 0.86, and I had overshot it. So I kept going, and I got to 0.857, and then I had overshot it. And I went backwards again, and I went 0.856. So you can see that in here at the final one, I got to 0.856991, and the Y is 0.999999, and my target is 1, and my accuracy that I originally called this with was 0.00001. I could have made it more. It wouldn't have made any difference. It still would have found the answer. It just would have been a little bit more accurate. And also, if I look at my variable explorer and I bring up answer, I can see that the answer it gives me that was returned is 0.85691, which, by the way, is the number in that last printout, 0.85691. Now, recap here. A lot of people look at this stuff and they're like, oh my God, I can't even imagine to understand it. It is not. This is not rocket science. You make a guess. The guess is too low, you guess higher. The guess is too low, you guess higher. The guess is too low, then all of a sudden you're like, oh, the guess is too high. You go back to the last guess and you take smaller steps. That's all I did. Not anything more complex than that. That's all I did. Now, of course, I had to write it in code. So, you got to learn it in a slightly different language. It's more accurate. But if you look at the code, it isn't that complex. I create a function that does the equation that we're looking to solve. And all the variables. I start at a value. I go to a maximum value by a step, looking for a target with an accuracy. If I find it, I say I found it, and I return the answer. If I don't find it, I go back a step. I reduce my step size, and I try again. Now, the cool thing here, iterative solutions. The function that I created calls itself. That is recursion. But recursion makes this easy. Now, you can't just recurse. You got to recurse with a new set of conditions. The new set of conditions were you go back one step and you reduce the step size. Okay? That's it. It's not, it's not brain surgery. It's not that hard to do. So don't cry. It's easy. I know you got to think about writing this stuff in Python, and you got to learn some stuff here. But think about what you're learning here. Matplotlib pyplot as PLT. Well, that gives me that function inside of, or that object inside of matplotlib, inside of pyplot. I'm going to call it PLT. I could have called it plot. I could have called it pilot. I could have called it anything. But what it does is it's a function, it's an object that has a plot function in it, and the plot function will take the two arrays and plot them, and I got this numpy stuff that makes it really easy to put all those numbers together. I made that plot in 3 minutes. You show me doing that by hand in 3 minutes. It ain't going to happen. You got some power here. Sure, you got to learn how to use it, but it's powerful use. And how often do you got to solve equations where you got to trial and error it? You're an engineer. Guess what? That's all the time. You do that. You live by the calculator. In my case, I live by my calculator phone, but it's still the calculator. So, you got this. Hopefully, you figured it out. I'm trying to make it simple on you. Think simple first. The complex stuff does come later. This is a pretty simple algorithm. The recursive solution, recursive iterative solution. In the specific case of an increasing function. That's what I solved. Now, there's other ones that can be more complex, like an increasing or decreasing function, but those are for a later date. Learn this one first. So, good programming, on out.